let's continue our study of equations of state. So we had just started talking about cubic equations of state, and I had introduced the van der Waals equation. Now, if one were to graph this, remember this is a third order polynomial in V, okay? Typically that's the way we do it, is so that you choose a pressure or a temperature, and then there's 3 roots for V. Okay, based on that. And if it has a third order polynomial, algebra tells me that there will be 3 roots, but they may not be distinct, they may not be real. So it's possible I have one real root and then I have a complex pair. Well, reality doesn't have complex pairs, so I have one real root, which means I know what the value is for the volume. Sometimes I end up with one real root that's repeated 3 times. Okay? Again, I know what the answer is. And then sometimes I have 3 real roots. Those are the stressful ones because I know nature has 1 solution, not 3 solutions. So if you were to take a look at the graphs, those cases where you have 1 real and complex root, it's saying that you have selected a temperature and done the graph. For a particular value of T, you can find what the volume is. Okay? If you happen to have that one where you have 3 or 1 root repeated 3 times, it turns out that that's always the point that goes directly through the critical point. And so all of those roots land right there at the critical point. The other guys, the graph looks something like this. So it comes down and it squiggles up and down. It has a minimum and a maximum. And this part over here looks fine. This part over here looks fine. It's this wiggly part in the middle that's the problem. So what happens here is that nature is doing a lot more than just finding the solution to this equation. Okay, we know that nature isn't sitting there calculating with its little calculator, but turns out that if you look at minimizing the energy or maximizing the entropy, you're going to find that this is going to split between those 2 extreme points. When I have 3 roots, the small one will be my liquid-like answer, my large one will be my vapor-like answer, and the middle root will be just non-physical garbage. Okay? In fact, what would happen is for this particular temperature, nature would come down and it would split and go over to forming a vapor and then continue this way. Nature would never do this wiggle. Okay? Now, so let's talk about other cubic equations of state. A lot of people have taken van der Waals' root idea and improved on that. So the next really major improvement that people ran with was the Redlich-Kwong equation in 1949. And it looks something like this. And basically, instead of just saying A over V squared, well, they said, first of all, A should vary with temperature. That attraction varies with temperature. And instead of V squared, that size parameter there really has a role, and so this is the way he included it, or they included it. 1972, Suave improved upon the Redlich-Kwong equation and came up with this, and he said, well, there is a component here, but there's also another parameter, and that does make the equation work a lot better. At roughly the same time, Pang and Robinson developed this equation, which is somewhat more complicated. The first term looks the same. You've got an A over T, but instead of V squared, they said that term there for the size of the molecule has a bigger role to play. Now, the Suave-Redlich-Kwong, normally called SRK, and Pang-Robinson, PR, are the 2 equations that are the most widely used equations of state out there for general purposes. There are many, many other equations that are used, but more of the rest of them are going to be for very specialized systems. They will tend to work very well for a system with high polarity or something like that. Now, all those constants, I mean, we went from PV equals RT, where we had one constant R, and we all know what that one is equal to suddenly an insane number of constants, and they're not even constant, they vary with temperature. Okay? So people have studied how to come up with those constants. And again, remember, this is semi-theoretical. So therefore, they are based on a theoretical principle with a little bit of empirical or data-driven modification to that. So, at critical temperature and pressure, the curve has 3 identical roots. That means that the first and second derivative both have to equal 0. You can just pretend there's a little equal 0 right there at the critical point. You can use this and use any of those cubic equations of state plus these 2 equations to develop formulas for the constants in those equations. Now, the one for van der Waals is actually not too horrible to solve on your own. If you have a free weekend, you might sit down and try that math. It's not that horrible. Turns out that these are the constants here, and they relate to the critical temperature and pressure because, remember, all of the definitions are based on the critical point having 3 identical real roots. And it turns out that at the critical point, Z is going to be 3/8. Okay, for everything. You can do this for all of the other cubic equations of state, but it turns out that what they really need to make it work is an additional physical parameter. So let's introduce the asymmetric factor. Pitzer's asymmetric factor was developed to deal with the fact that molecules aren't always round. So we have a term that's going to take account of the fact that they don't have infinitesimal size. We have a term that's going to take into account the effect of interaction of molecules. But we needed some way to talk about the fact that, wait a minute, even if they are small, but they're not round, if they're a little bit egg-shaped or if they're really long, that's going to be a very different interaction. Because if I have 2 molecules that are, let's just say they look like little pencils, okay, long, thin molecules, and they bump into each other end to end, it's very different than bumping into each other side by side or the point of one and the side of another. So we need to know how non-round they are. So the asymmetric factor does that for us. Now, by definition, what it means, or how it's defined, is you find the reduced pressure, P over P critical, at a reduced temperature, T over T critical, a reduced temperature of 0.7. So figure out what the pressure is at that time, so the vapor pressure, so at equilibrium, and then take log base 10 of that number, subtract it from -1, and you have the Pitzer's asymmetric factor. Now, if you're using Smith-Van Ness, then pages 680 to 681 have values of omega. In general, kind of what you're going to see is noble gases, omega 0, because they're just one molecule, so they truly are round. Most molecules are going to end up being positive because that vapor pressure term is going to be a larger negative than the -1. So when you subtract it, it's going to make a positive answer. And the smaller the molecule is, the closer it is to 0, essentially. Hydrogen is going to be our kind of odd man out. He has a negative asymmetric factor. Okay? It is 2 very, very tiny little atoms together in virtually a spherical form, and it ends up with a negative asymmetric factor. But this is data that you can look up. You could calculate it if you needed to. Now, in order to make all of the math, this really does make it easier, trust me. Okay, but at least there's a uniform approach to solve all of these things. The authors of this textbook have the form of the equation as shown on the screen. It's got the RT over V minus B because they all have that. And then it's got some sort of function of temperature on the top, and V maybe plus something B, maybe not. Okay. If you use this equation right here, turns out that they are really all the same if you use the constants shown in this table here. Sometimes those constants are truly a number. Okay, these are the ones that could be developed using the math. And then some are done by fitting a lot of data for a lot of different systems. And we end up with these expressions here. And the alpha, the numerator of this attractive term, is going to be the one where I use the asymmetric factor. It also does have the TR in it. Remember, that's the actual temperature divided by the critical temperature. And above all else, make sure that you are using absolute temperature in all of these. This is just like using the ideal gas law. So, okay, that may look very intimidating, that screen, but it's really helpful because what it means is that all these equations basically are the same, and all of them can be solved in essentially the same way. So if you were to try and solve a cubic equation, a third-order polynomial, something like this, I mean, there is a solution for the answer. One answer is going to be this, where you're taking these lovely expressions, okay, and that gets you one root, and then you take x minus that one root and divide it into the original polynomial, and then that gets you a second-order polynomial, and now then you can use the quadratic equation to solve. And you are welcome to do this anytime you want to. However, people have been working with these equations often enough that they took the time to come up with a more streamlined technique. Now it is iterative. Okay? So we know, first of all, that we want the vapor-like root and the liquid-like root. We don't want that middle root. We also know that if I am expecting a vapor, because physically I've seen the system, then that vapor-like root is probably the only one I want. Okay? So there are some approximation methods that are iterative that can be used, and computers don't mind the brute force approximations. Okay? What is helpful, however, is basically to start with the right value. Remember, I'm going to get three answers. I want either this one or this one. I don't want the middle one. And so therefore, if you start with an answer that's close to the answer you want, iteration is going to take you to the answer you want most of the time. So if you're looking for something that's like a gas, vapor-like, put in z equal 1. Say, I think ideal gas law would be a good approximation. So if you've got an equation in z, put in z equals 1. If you have an equation in v, put in v equals RT over P. Use the ideal gas law as your first guess. If you're looking for liquid, that one's a little harder to guess at what you want. You know it's going to be a smaller number, but you don't know what it is. So v equals b, or that BRT over P term, or beta in the table, is going to be a good first guess. Now that probably seems a little confusing, so let's look at this a little bit better. So they have an outline in the book that tells you exactly how to find all these things. But so use the constants in that table a few slides back. Calculate the beta, calculate the q, put those into this equation here for z. Okay? Now if you are looking for the vapor-like root, put z equals 1 on the right-hand side. So you can put z equals 1 here, you're going to put z equals 1 here, z equals 1 here, and you're going to use that to calculate this. Z equals something in terms of z. We're going to put in a guess on this side, calculate this one. That new answer I get, I'm going to plug that in the next round. I'm going to put that answer in here, here, and here, calculate a new z. And keep going this until you get virtually no change from one step to the next. And that's going to be your answer. Okay? This tends to converge very quickly. Now for liquid-like roots, it's a little harder, but again, you're going to calculate the beta and the q. You're going to plug them into this formula. You're going to start with a guess of z equals beta. You're going to plug that in over here. You're going to get an answer here. You're going to take that answer, plug it in over here, get an answer here, and you're going to repeat that until you get virtually no change. And it's going to take you quite a while. Okay, I'm just going to warn you. Now, there is an alternate form. If you don't want Z, you can calculate V. There are different forms of this equation. Okay, your choice. So I have an Excel file that does this for a couple of examples. So first one of these is methane at 250 Kelvin and 50 bar. And since this is above the critical temperature, this is the data for methane up here, it's above the critical temperature, so I think that this one will be vapor-like. Okay, it'll be a single gas or a single phase, and it will tend to be gas-like because it's at a fairly high temperature. High temperature tends to be more like a gas. And so I put in my numbers. I did this using both van der Waals and Peng-Robinson, I believe. I have these numbers. I have all of my given data, just found in data booklets. I compute TR and PR. The van der Waals equation takes some time to actually look at this, but I calculate A and B using those formulas with R, TC, and PC. Now I can choose any kind of R I want to, but I do want to make sure that it's working with these units up here, so I have done that. And I put in a guess for V. I put in RT over P for my guess for V, again assuming an ideal gas. And I just did iteration on the ideal gas or on the van der Waals equation until I got 0, and I made Excel do all the hard work. Okay, try it out. If you need some more help on using Excel to do some of these things and you don't have another software that you like to use to do this, please contact me. I would be happy to, we can set up a conference and we can work on it together. Now, the Peng-Robinson equation, I had to calculate a whole lot more stuff, not just a simple A and B. I had to do sigma, epsilon, omega, psi, alpha, beta, and Q, and then I put in a guess for Z. I use that equation. I use this, compute Z again, use this, compute Z again, and it took roughly 10 steps, and I got 0.81173, no change, so I used that and computed V equals ZRT over P. Okay, so that's using this on a gas. On a liquid, I did methane at 185 Kelvin and 50 bar. So this one is going to be below the critical, so I think that this could possibly be, liquid or gas. So I checked the pressure and notice that the pressure is higher, so I've got something that's cooler than the critical temperature, but at a higher pressure. So these have been squished together. So this is going to be more liquid-like, I think. Okay? I'm going to therefore use for the guess the B term, okay? And I just went through and did the same formula there using my first guess of B. And using the Peng-Robinson, I did this, and this actually goes on, if you look at the real file, goes on about another 10 or 15 iterations. Eventually, we get an answer of V equals 0.1257 liters per mole, which is a liquid-like value. But my really big takeaway here, besides looking at a lot of random numbers, is that gases are going to work pretty well here. Liquids, not so much. Okay? It's not that it can't calculate for liquids. It's going to be very hard to calculate for liquids, because for gases, all of these were based on ideal gas law. So observations of gases. So they're going to be much easier to predict the behavior of gases. Now, very quickly, I want to cover one last thing, empirical equations of state. Empirical equations of state is a huge category, but an empirical equation of state is not theoretical, like the virial, or semi-theoretical, where they take theory but then make it fit data. An empirical equation totally is done by fitting data. Okay? There are many, many of these. The one that is best known is taking the virial equation of state form and trying to fit data, and it turns out that the Benedict-Webb-Rubin, BWR, is probably the best known of all of the empirical equations of state. There are actually empirical forms of Peng-Robinson, SRK, etc. So this, and the trick here is simply that you got to have data. It's not going to be easy and pretty to solve, so you're going to use an iterative technique. Okay? Otherwise, it's just fact. Here it is. Here's another equation. So at this point, I just want to remind you we have completed Unit 1. I need you now, if you're taking this course for credit, to schedule a time with me to take the exam. If you're doing it away from Rolla, you might want to set up an appointment with a testing facility before you contact me so that we know what kinds of parameters we're working with. Now, I've designed the exam so that you could complete it in 1 hour, but I am going to allow 2 hours to take the exam just because this is sort of unusual circumstances without me there to ask questions. The exam is open book, open notes, but closed computer resources. So if you have, things out of the book that you want and you have a computer version of the book, you'll need to print those out or borrow a book from somebody else. Now, don't worry about data tables. In order to make sure that everyone has the same information, I will provide data tables with the exam. So, thank you for your attention, and when we get back together, we're going to be looking at those topics that are much more specific to chemical engineering.